We will discuss in the last theorem, theorem 8.16, Parsevals theorem. F in the Fourier series in the convergence ആണ് discuss ചെയ്യുന്നത്. The statement of theorem is suppose f and g are Riemann integrable functions with period 2π, and the Fourier series of fx is this one. Cn's are the Fourier coefficients of f, and gamma n's are the Fourier coefficients of g. Then we have limit n tends to 1 by 2π integral minus pi to pi mod fx minus Sn fx whole square dx equals 0. The meaning of the statement is you might have heard about the 2 norm. So with respect to 2 norm, this sequence of particles of Fourier series converges to f of x. So that means this when you take whole ratio 1 by 2 on the left side, we'll get this is norm 2 norm of f minus Sn fx. 2 norm tends to 0 as n tends to infinity. That is the meaning of this statement. And this is the 2 norm. And if we have f and g, then this integral will be summation minus infinity to infinity Cn and then conjugate. And if you replace this f g by f itself, then this becomes norm f square. So the norm f square is obtained by summation minus infinity to infinity Cn square. So that is this one. That means Fourier series converges to the corresponding f if f is Riemann integrable to pi periodic function with respect to 2 norm. Okay, so with respect to 2 norm, we can get the convergence of this Fourier series. To prove this Parsevals theorem, we need to refer to important results. One is discussed in chapter 6 as example 12. Suppose f belongs to R alpha and epsilon greater than 0, then there exists a continuous function g on AB such that 2 norm f minus g is less than epsilon. So that means with respect to 2 norm, every continuous function every continuous function g on AB from a closure of integrable functions. So that is the first result. And the second result is Schwarz inequality. You might have studied this in your function analysis class. Integral a to b f g d alpha is equal to integral a to b less than or equal to integral a to b mod f square d alpha whole is 1 by 2 integral a to b mod g square d alpha whole is to 1 by 2. So these are the references. So using these references, you can prove Parsevals theorem. So first of all, now we start with an epsilon greater than 0. Before that, we write 2 norm. What is 2 norm here? This is norm 2 norm h. So this is the by definition. This is 1 by 2 pi. This 1 by 2 pi to normalize that, so minus pi to pi mod h of x square dx whole raised to 1 by 2. So this is the value of 2 norm, 1 by 2. Okay, so this is the proof. Now we have we start with an epsilon. Let epsilon greater than 0 be given. We are given that f belongs to Riemann integrable functions, and f of pi is equal to f of minus pi because it is a 2 pi periodic function. Then using this the reference given here, if you take alpha of x equal to x itself, then this becomes an element of Riemann integrable functions. Then use this, then you can get a continuous function. So using this result, you can get a continuous function. Then there exists a continuous function, continuous 2 pi periodic function, we named it as h rather than g. H with the property that norm of f minus h. Instead of writing g here, I put h here. To norm is less than epsilon. Okay, so this is the first statement. Now we have the previous theorem, theorem 8.15, corresponding to every integrable, every continuous 2π periodic function. Here this asserts that there exists a continuous 2π periodic function, and corresponding to that 2π periodic function there exists a trigonometric polynomial. Okay, so corresponding to that epsilon, we take this h as the continuous 2π periodic function. Then using the previous theorem 8.15, there exists a trigonometric polynomial, say p of x, such that this modulus of this quantity is less than epsilon for all x. Okay, so by considering this, then we can easily convert it to norm. That is, when you consider this one, then you can get square is also less than epsilon square. So we have h of x. For simplicity, we write h itself, h minus p square is less than epsilon square. Then integrate this from a to b. This is integral minus pi to pi, not a to b, minus pi to pi, minus pi to pi. This is minus pi to pi. Then multiply it with 1 by 2 pi. Here we have 1 by 2 pi. Then the same inequality retains, and this will become, by taking epsilon square out, then this will become epsilon square itself, because the integral will be 2 pi, so we can cancel 2 pi from the numerator and denominator. So this is this one, and by taking whole raised to 1 by 2 on both sides, this reduces to whole raised to 1 by 2, that is equal to epsilon. So which denotes the norm of h minus p, 2 norm of h minus p, which is less than epsilon. So as a consequence of this, you can get h minus p, 2 norm h minus p is less than epsilon. Okay, now we have, if this p has degree, if this p has degree n naught, that is a trigonometric polynomial, then theorem 8.11 shows that norm h minus SMH, the 8 minus 11 is the mean square difference. We already proved that with respect to 2 norm, the sequence of partial sum of Fourier series is very close to the corresponding function. So it's if you take the corresponding Fourier series of sequence of partial Fourier series of h, then we can get h minus Sn of h with respect to 2 norm is less than or equal to h minus any trigonometric polynomial. Okay, if we have trigonometric polynomial is less than epsilon, and we can say that the corresponding Fourier series or a sequence of partial sum of Fourier series is very close to this h. So since this is less than epsilon, we can write this is also less than epsilon. This is with respect to 2 norm. Now we have, so we can consider this inequality and this, and we will establish one more. Now we have proved inequality in the theorem 8.11 itself. That is integral minus pi to pi mod Sn x square dx is always less than or equal to integral minus pi to pi mod f of x whole square dx. We have proved this one, and if we replace this f by we replace f by h minus f in this, we can get minus pi to pi modulus of this is Sn h minus f Sn comma x. This is in fact Sn fx. instead of f we replace that by h minus f. Square dx is less than or equal to minus pi to pi. This can be written as mod h minus f square dx. Then consequently, by taking this can be written as Sn of h minus Sn of f. Then consequently, by taking the power raised to 1 by 2 on both sides, we have this is the difference between norm of the difference between Sn h x minus Sn f x with respect to 2 norm. That is same as which is same as this norm of Sn h minus f with respect to norm, which is less than or equal to this quantity is less than or equal to norm of this 2 norm of h minus f. So this is 2 norm of h minus f with respect to 2. This is true for and we have seen that this quantity h minus f is less than epsilon by 2, less than epsilon due to this, the first result. Then we write this is less than epsilon. Okay, now we use triangle inequality to get the required result. The first result, that is what is f minus Sn, we start with this Snf, that is Snfx. Then this is the Fourier series of the sequence of Parsevals Fourier series of f minus this quantity, and this is less than or equal. First of all, we can insert some terms to this one, that is f minus we first write h, then we insert h, then we insert Snh. Then we can insert these terms to this norm, and using the property of the norm, the triangle inequality, we can write it as this is norm f minus h 2 norm plus norm h minus Sn of h with respect to 2 norm plus the last one norm Sn h minus Sn f with respect to 2 norm. Each quantity is less than epsilon, so this is less than 3 epsilon. Okay, since this epsilon is arbitrary, we can say that this Sn of f converges to f as n tends to infinity. Okay, so this proves the first statement of the theorem, and next we will show that what is 1 by 2 pi minus pi to pi Sn of f g conjugate dx. Okay, so we need to prove that this is summation minus n to n Cn gamma n conjugate, and taking n tends to infinity we can get the required result. So first we write this is equal to summation minus n to n, we write Cn first, this is Cn 1 by 2 pi integral minus pi to pi, this is e power I n x g of x conjugate dx. This is due to the definition of Sn of x. We have Sn of f is summation minus n to n this Cn e power I n x. Okay, so if we multiply it with g conjugate on both sides and take the integral, then interchange the integral and summation, since it contains only finite number of terms, so then you will get this one. Okay, and we can write this as the right hand side. When you observe the right hand side, that will give the Fourier coefficient, the conjugate of the Fourier coefficient of g. Okay, because this can be written as minus n to n Cn 1 by 2 pi integral minus pi to pi g of x e power minus inx whole conjugate. Okay, so when you write like this, then the bracket will be gamma n conjugate. Bracket is gamma, so this is gamma n conjugate, because that is a Fourier coefficient of g. Okay, so this becomes Cn gamma n conjugate. Okay, as n tends to infinity on both sides. Here if we let n tends to infinity, then this converges to corresponding f. So this is a sequence of partial sum of Fourier series of f. So this tends to this integral tends to integral 1 by 2 pi integral minus pi to pi, and this becomes f of x, and this is g bar x dx. That becomes as n tends to infinity, this becomes minus infinity to infinity cn gamma in conjugate. Okay, so this proves the second result. For the third result, we put f of x equal to g of x in this expression. So that will be by putting f of x equal to g of x, then we can get 1 by 2 pi minus pi to pi. This f of x into f of x conjugate dx equal to summation minus infinity to infinity cn conjugate, because cn is the Fourier coefficient of f. So this will give minus infinity to infinity mod cn square. Okay, so this proves the third result as well. Now with this we can conclude the syllabus. The fourth, with this we can complete the module 4. So please try to do the problems of this from the exercise, and if you have any doubt, then please come up with your doubt. We can schedule a Google Meet for live interaction. Otherwise we can go for the exam. All the best. Thank you.